One of the most profound impacts of artificial intelligence is not just in automating tasks or improving efficiency, but in accelerating the pace of scientific discovery itself. For centuries, scientific progress has depended on a combination of human intuition, experimental work, and incremental theoretical development. Today, AI is beginning to transform this process by acting as a powerful partner in hypothesis generation, simulation, pattern recognition, and optimization. Instead of replacing scientists, these systems extend human capability, enabling exploration of complex systems that were previously beyond reach. At a fundamental level, science is about discovering patterns and underlying laws from data. Whether in physics, biology, or climate science, researchers collect observations and attempt to build models that explain and predict behavior. Artificial intelligence, particularly machine learning, is exceptionally well suited for this kind of pattern discovery. Modern AI models can process massive datasets, identify subtle correlations, and propose relationships that may not be obvious to human researchers. This ability becomes especially important in domains where the data is high-dimensional, noisy, or incomplete. One of the key ways AI accelerates discovery is through simulation. Many scientific problems involve systems that are too complex to study purely through experimentation. In physics, for example, simulating particle interactions or quantum systems can be computationally intensive. In climate science, modeling the Earth's atmosphere and oceans requires solving large systems of equations across space and time. AI models can approximate these simulations, dramatically reducing computational cost while maintaining acceptable accuracy. This allows researchers to explore more scenarios, test more hypotheses, and iterate more quickly. In biology, the impact of AI has been particularly visible in the field of protein folding. Proteins are fundamental to life, and their function is determined by their three-dimensional structure. Predicting how a protein folds based on its amino acid sequence has been a long-standing challenge. Traditional methods required extensive laboratory work and could take years to produce results. AI models have changed this by learning the mapping from sequence to structure, enabling rapid and highly accurate predictions. This breakthrough has significant implications for drug discovery, disease understanding, and biotechnology. Beyond protein folding, AI is transforming other areas of biology as well. In genomics, machine learning models analyze DNA sequences to identify genes, regulatory elements, and mutations associated with diseases. In drug discovery, AI systems can screen vast chemical spaces to identify candidate molecules with desired properties. Instead of testing compounds one by one in the lab, researchers can use AI to narrow down the search space, focusing experimental efforts on the most promising candidates. This reduces both time and cost, accelerating the development of new therapies. In materials science, AI is being used to discover new materials with specific properties, such as strength, conductivity, or thermal resistance. Traditionally, materials discovery has been a slow and experimental process, involving trial and error. AI models can learn from existing data and predict the properties of new combinations of elements or structures. This enables the design of materials tailored for specific applications, such as more efficient batteries, stronger composites, or better semiconductors. The ability to explore vast design spaces computationally opens up possibilities that would be impractical to achieve through experimentation alone. Physics is another domain where AI is making a significant impact. In experimental physics, large instruments such as particle accelerators generate enormous amounts of data. Identifying meaningful signals within this data is a challenging task. Machine learning models can be trained to detect patterns associated with rare events, helping scientists make discoveries more efficiently. In theoretical physics, AI is being explored as a tool for discovering new equations or approximations that describe complex systems. While this is still an emerging area, it suggests a future where AI contributes not just to data analysis, but to the formulation of scientific theories. Climate science represents one of the most critical application areas for AI-driven discovery. Understanding and predicting climate behavior involves integrating data from satellites, sensors, and historical records, as well as modeling interactions between the atmosphere, oceans, and land. AI models can process these diverse datasets and improve predictions of weather patterns, extreme events, and long-term climate trends. They can also be used to optimize energy systems, model the impact of policy decisions, and identify strategies for mitigating climate change. Given the urgency of global environmental challenges, the ability of AI to accelerate insights in this domain is particularly valuable. Another important aspect of AI in scientific discovery is hypothesis generation. Traditionally, scientists develop hypotheses based on existing knowledge and intuition, then design experiments to test them. AI can assist by analyzing data and suggesting potential hypotheses that may not have been considered. For example, in biomedical research, AI might identify a previously unknown relationship between a gene and a disease. These suggestions still require validation, but they can guide researchers toward new directions more quickly. Automation of laboratory processes is also becoming more common. Robotic systems controlled by AI can conduct experiments, collect data, and adjust parameters in real time based on results. This creates a feedback loop where the system continuously learns and improves its experimental strategy. Such self-driving labs can operate faster and more efficiently than traditional setups, enabling rapid exploration of complex experimental spaces. Despite these advances, there are important challenges to consider. One of the main issues is interpretability. Scientific discovery is not just about making accurate predictions, it is about understanding underlying mechanisms. Many AI models, particularly deep learning systems, are often described as black boxes. While they can produce highly accurate results, it can be difficult to explain how they arrived at those results. Developing methods for interpretable AI is crucial for scientific applications, where transparency and reproducibility are essential. Data quality and availability are also critical factors. AI models are only as good as the data they are trained on. In some scientific domains, data may be scarce, noisy, or biased. Ensuring that datasets are representative and well curated is essential for reliable outcomes. In addition, integrating data from different sources and modalities presents technical challenges that require careful design. Another consideration is the collaboration between AI systems and human experts. AI can process data and identify patterns at scale, but human scientists bring domain knowledge, intuition, and critical thinking. The most effective approach is a hybrid one, where AI augments human capabilities rather than replacing them. This requires designing interfaces and workflows that allow seamless interaction between humans and AI systems. Ethical considerations also play a role. In areas such as drug discovery or climate modeling, decisions influenced by AI can have significant real-world consequences. Ensuring that models are used responsibly, with appropriate validation and oversight, is essential. There is also a need to consider issues such as data privacy, especially in biomedical research. From a technological perspective, advances in hardware and infrastructure are enabling the growth of AI in science. High-performance computing, specialized accelerators, and cloud platforms provide the computational power needed to train and deploy large models. At the same time, improvements in algorithms and architectures are making these models more efficient and scalable. Looking to the future, the role of AI in scientific discovery is likely to expand even further. We may see systems that can autonomously design and conduct experiments, generate and test hypotheses, and integrate knowledge across different domains. This could lead to a new paradigm of AI-augmented science, where the pace of discovery is significantly accelerated. At the same time, the human element will remain central. Science is not just about data and models, it is about curiosity, creativity, and the desire to understand the world. AI provides powerful tools, but it is the collaboration between humans and machines that will drive the most meaningful breakthroughs. In conclusion, AI is transforming scientific discovery by enabling faster data analysis, more efficient simulations, and new approaches to hypothesis generation and experimentation. From protein folding and drug discovery to materials science and climate modeling, the impact is already significant and continues to grow. While challenges remain in areas such as interpretability, data quality, and ethical use, the potential benefits are enormous. By combining the strengths of AI with human expertise, We are entering a new era where scientific progress can be accelerated in ways that were previously unimaginable.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.